Hello, this is Tommy. Welcome to Chatomics. So in my previous video, I showed you how to make a heat map using the R package complex heat map. So in this video, I'm going to show you how to make a perfect heat map using real RNA sequencing data. So the data set we're going to use is from Geo. So by the way, this R Markdown file will be, the link will be in the description of this YouTube video. So go and download it and follow the tutorial. So the data set we're going to use is RNA sequencing data of these two genes knockout in SW480 cell line under normoxia and hypoxia. So SW480 is a colon cancer, adenocarcinoma cancer cell line. And you see here there are multiple actually conditions here. So they have the sgRNA control and also the sgRNA knockout. So just for simplicity, we will focus on the control condition. So there's no knockout, but let's compare hypoxia condition versus normal normoxia condition. So you can directly click here and download the count matrix, but let me show you how to download this count matrix in the command line from the FTP. So in this link, it shows you how to download Geo data from command line from the FTP sites. So according to this instruction, and you will see the data actually resides in this link. So the link is also in the R Markdown file. So what we will do, we will use wget to download the file. So let's go to the folder. So this is usually I set up the projects. So I have a data folder only contain the raw data. The results folder contains the figures or intermediate results, and the scripts contains all the R Markdown files. So let's change directory to the data folder cd data and press enter. So if you do ls again, there's nothing there. And let's copy this command and press enter. So you do ls again, you see this file is downloaded to your local computer. So after you download a file, usually on command line, we'll look at how the data looks like. So using less command, because this is a compressed file, I will use zless and capital S. So this capital S option, so it will not actually wrap the lines if it's too long. So I can show you how it looks like using this. So essentially we have the first column is the gene column, and the other columns are the samples. And those entries are just the raw counts for each sample, for each gene. So you can press Q to quit. So if you don't use the capital S argument and just use zless, and you see because the first row is too long and now it's wrapped. So that's why I always use zless and capital S to look at a big file. Okay, but I'm going to actually show you some other very useful command line utility called CSV-TK, and you can install it from this link here. And this is a tool to deal with CSV file and TSV files on the command line. So I will use the CSV pretty command, and -t tells it's a tab delimiter file. And let's do it on the command line. And now you see, and you can use a left arrow and the right arrow to move around the file. And you see now it's aligned really well. Okay, press Q to quit. And the next command is called CSV TK headers. And it will show you all the column names from this file. So the first column is gene, the rest are the sample names. And for the demo purpose, I will only use this 2 sample and also this 2 sample on the hypoxia condition. So what we will use is the CSV TK cut command, and the first column is the gene column, and the rest 4 columns are the 4 samples. I pipe it to the head command to see how it looks like before I save it. So yeah, it is as expected. The first column is gene, the rest 4 columns are the 4 samples that we are going to use for this demo. Okay, so now we will save it into a new file. So now I use this greater than sign and save this file, this new file into the raw counts.tsv file instead of printing out in the terminal here. Okay, so it's not printing out anything, and if you do ls to list all the files again, then you see this new files here. Okay, and this is the file that we're going to use for DSeq2 to find differentially expressed genes between hypoxia versus normoxia. Okay, let's go back to R. First, let's load those libraries and read this raw counts file into a data frame. Okay, so here I use this function called here. So here is a little magic here. So this one will, if you just run this command, it will show you the full path for this file on your local computer. So on your computer, I mean, the first, this path here may be different, right? Because this is on my own computer. But if you do git clone of the whole repository, like this git compile tutorial directory, and if you run the same command like here, it will figure out the absolute path on your own computer. So this command works on my computer, but it also works on your computer. So it increases the reproducibility of your scripts. Okay. So after you read into this data frame, always look at the first 6 rows using head command, and this is as expected. And now we will actually turn this data frame into a matrix. So we actually remove the first column here and turn it to as a matrix. Let's take a look. Okay, now it removed the first column, but we want to add the row names as the gene names. So let's do this. Let's look at it again. Now the row names are the gene names, column names are the sample names, and this is ready for DSeq2. So, but before that, we also need to make a data frame for the metadata. So just indicate this first 2 samples are normoxia condition, and the next 2 are hypoxia condition. So I just make a new data frame. This is a data frame with a single column, and we want to add the row names as the sample names. Now look at it. So now it's just a single column data frame with normoxia, hypoxia with corresponding sample name as the row names. Now we can follow the DSeq2 tutorial. I highly recommend you to read the online tutorial. It's quite comprehensive. Okay, so we just feed the count matrix and the metadata into DSeq data set from matrix function. And design essentially just tilde sign and condition. So we want to compare hypoxia versus normoxia. So those are all routine DSeq2 processing steps. So you can just follow it. we run DSeq, and then we run the differential expression. So just one note here. So here you want to specify the contrast. So this format, so you can read the help for this function results, and you see how to specify the contrast here. So this is just a character vector of 3 elements. This is the column name of your metadata that you want to use, and then hypoxia is the numerator, and the normoxia is your denominator. So you want to compare hypoxia versus normoxia. Okay, let's look at the first 30 rows of the differentially expressed gene list. So I turn it to a data frame, and then arrange rows by adjust the p-value, and then the log2 fold change. Okay, those are the first 30 genes that are identified differentially expressed between hypoxia versus normoxia. So for any data analysis, you always want to double check during your analysis. So if you see this gene is the most differentially expressed gene with really big log2 fold change, a small p-value, adjust the p-value, you want to see whether it's real or not, right? So you see, hypoxia. Indeed, you see IGF-BP3 is a hypoxia-inducible gene. That indicates your analysis probably is good. And I also see, for example, PGK1, I know it's a known hypoxia-inducible gene. It's also in the top gene list. Okay, now we will actually select the significant genes just from this table. So I use this p adjustment value smaller than 0.01 and absolute log2 fold change greater or equal than 2. And this is kind of arbitrary, so you can define it by yourself. Okay, see how many significant genes that are left after we filtered the table. Okay, around 620 some genes here. So we will table it first for now, and we will use those genes to make perfect heat map in the end. So I would like to do actually some principal component analysis. For any data analysis, I will do that just to verify whether the experiment works or not. So we first run the VST function to do normalization. And we can do plot in DSeq2. There is a function called plot PCA, and we can run it. And in this PCA, you see the first principal component explains almost all the variance here, and you see those 2 samples are on the hypoxia are close to each other, and those 2 on the normoxia are close to each other. So this probably shows you this experiment worked and your analysis is good. Of course, plot PCA is just a wrapper from DSeq2, so you can always make a PCA plot by yourself. So what you can do, you can first get the normalized counts using this line of code, and then you can calculate the principal components using PRComp, this function. So remember, if you don't know how to use it, always use question mark PRComp to find the help. Okay. So, and if you look at the names of the this object after you calculate PCA, they are like STD, V, rotation, center, scale, and X. And what we'll use is the X component here. So the first component PC1 and the second component PC2 here to make the same actually PCA plot like this. Okay, we just create a new data frame, and those 2 just contain the 2 principal components, and then just some simple actually ggplot2 function. And you see actually those two are hypoxia condition. Those 2 samples are on the hypoxia condition. 0, 1, 0, 2, those are on the normoxia condition. It looks very similar to the old principal component plot from DSeq2, but it's not almost the same, right? I mean, the x-axis looks like very similar to scale, but the y-axis is a little bit different. So what's going on? So if you look at the help of plot PCA, and you'll see actually it's using the top 500 genes for running the PCA. So in DSeq2, and in our own customized analysis, we are using all the genes. So in fact, if you go to this link, go look at the source code of DSeq2, you will see how to select the top 500, the default like most variable genes. If you follow that, you will actually have the same results. Okay, now let's make a perfect heat map. Now is the time. Okay, so we still use normalized count matrix, but now we are only subsetting the significant genes, this 600 some genes. So if we run this line of code, and if you look at the dimension of this matrix is 623 genes and 4 samples, 2 normoxia and 2 hypoxia. So in my last video, I also show you why we need to scale the data, right? So let's, if you don't know why we're doing this, go back to the previous video. I will have a link in the description, and then you will need to watch the old video. So let's do that using Heatmap with capital H from the complex Heatmap package. See, so now you get actually a perfect looking heat map, right? So those genes, those 2 samples are hypoxia, those 2 samples are on the hypoxia, those 2 samples are on the normoxia. And you see those genes are actually those genes are downregulated in the hypoxic condition, and those genes are upregulated in the hypoxic condition, right? So this is really a perfect looking heat map, right? But it is because that we select those genes by performing the differential expression test first. So there's no surprise at all that we have a perfect looking heat map. Okay, so we can do a little bit more to just make it a little bit prettier. For example, remove the row names, and also add a column annotation to show, okay, which samples are on the normoxia and which are samples on the hypoxia. Now we can read it from the sample name, but it would be nice to have a column annotation bar here. So in complex heat map, it's really easy actually to add those column annotations. So remember this data frame that we used, the metadata we used when we construct the DSeq2 object. So in complex heat map, you can use this function called Heatmap annotation, and you can supply a data frame and into the first argument, and then you can specify the colors for each of the condition. For example, you can say, okay, red is hypoxia and blue is normoxia. Okay, so you do that. Okay, we don't need this. Don't need this. Okay, so let's do the heat map again, but now we actually supply this column annotation into this top annotation arguments, and we'll show row names for us because there are too many gene names here, and give the heat map a nicer name here. Okay, let's do it. See, now it looks much better. Now you have this row, this column bars here to show this is from hypoxia, those two samples from normoxia. Yeah. And as I mentioned, that scaling is important because if we don't scale the data, for example, like we just use the significant matrix and see how it looks like. Now it's showing the raw, the scale, actually not scale, the normalized expression value, but then you can't see the differences between those two conditions, because the purpose of scale is really to make the genes that showing the same pattern. They're high in normoxia or low in normoxia, high in hypoxia or low in hypoxia. They're really distinct. So if you do the scaling, because you do the scaling across all the samples for the same gene. Okay, let's try it again. Yeah, it's really fulfilling to see a perfect looking complex heat map. Okay, that's it for today. I hope you enjoy it. If you like this content, please subscribe and also leave comments. I will make more videos that you want.